In this video, we're going to take a closer look at valence electrons. You'll recall that valence electrons are the electrons in the highest occupied energy level, and they can be predicted from location on the periodic table. With respect to valence electrons, again, the most stable arrangement of valence electrons is a full S and P sublevel of the highest energy level, which accounts for 8 valence electrons, or what we refer to as an octet. As a general rule, when forming compounds, particularly representative elements are going to tend to react in order to obtain 8 valence electrons, or a noble gas electron configurations, because having 8 valence electrons is a fundamentally stable arrangement of electrons. So let's look at some electron configurations in the third period. But before that, quickly see if you can recall what are the 3 rules that allow us to fill electrons, typically as up or down arrows to represent spin, into an Aufbau diagram. Take a second, maybe see if you can jot them down in your notes without looking them up. Okay, first rule, of course, Aufbau principle, says that we have to fill from lowest energy to highest energy. Second rule is the Pauli exclusion principle, which says that no box here can contain more than 2 electrons, provided they are opposite spin. And Hund's rule says we have to fill orbitals of equal energy, any sublevel that has more than 1 orbital, 1 in each orbital with like spin before pairing. So let's take a look at sodium. Check your periodic table, see if you can find the number of valence, or the number of total electrons, for sodium. And hopefully you see it as 11. So let's start filling in the boxes. Put the first one in the 1s, the second one is going to go in the 1s with opposite spin. Next one will go in the 2s. Notice we started down spin this time. Again, it doesn't matter as long as the second electron is always opposite spin. Then Hund's rule, that's 4. We go 5, 6, 7. 1 in each orbital with like spin before pairing. There's 8, 9, 10. Now we have a full 2p and 1 in the 3s. And our configuration there is going to be 1s2, 2s2, 2p6, 3s1. Highest occupied energy level is the third energy level, and there is 1 electron in the third energy level, so we'd say sodium has 1 valence electron. Here we have magnesium, and magnesium has 12 valence electrons. If we drop all of those in there, again, look at our electron configuration. Again, we could also put neon in brackets there in 3s2. But the highest occupied energy level is still the third energy level, and there are 2 electrons. The third energy level, so magnesium has 2 valence electrons. We can now look at aluminum. 1s2, 2s2, 2p6, 3s2, 3p1. Third energy level is still the highest occupied energy level, but we count both the 3s and the 3p to get us to the third energy level. And if you look at your periodic table, you'll notice that we labeled that column 3a. So the representative elements are actually labeled. The A groups, when we label them that way, the A groups have the number of valence electrons in their A group. Silicon would have 4 valence electrons, 3 in the 2, or 2 in the 3s, 2 in the 3p. Phosphorus would be 5 valence electrons, 2 in the s, 3 in the p. Sulfur would have 6 valence electrons. So we move across the third period here. Then we get to chlorine, which would be 7 valence electrons, 2 in the s, 5 in the p. And then we get ourselves to argon. With 2 in the s, 6 in the p, it has 8 valence electrons. And of course, that 8 valence electrons is our octet, an incredibly stable arrangement of electrons. Okay, so now we're going to look at a thing called electron dot structures. It's another way, other than the Aufbau diagram with the arrows, to model valence electrons. And so first, let's take a look at nitrogen here. So look on your periodic table. I want you to write down a big N somewhere on your notes, and then I want you to look at your table and see if you can figure out how many valence electron nitrogen has, and then maybe just write that off to the side in the margin. Go ahead, pause the video, take a look, and write that number down. hopefully you were able to sort out that nitrogen has 5 valence electrons. So electron dot structures, we're just going to put dots around the symbol for the element. And we're going to put one on each side. We think top, bottom, left, right, before we can go back and pair up. So that's going to be the first dot, second, third, fourth, and then the fifth. Now, we don't have to start at the top. You can start on the right. You don't have to start on the right. You can start on the bottom. You don't have to go clockwise. You can go counterclockwise. You can go left, right, and then top, bottom. We could have put the double electrons on the bottom. We could have put them on the left. The key here is that you need 3 single electrons and 2 paired electrons. All right, so that would be a dot structure for nitrogen. So let's see if we can apply that same concept here to these elements. So you need to find somewhere on your paper, write out each of these element symbols, grab your periodic table, and see if you can go about making a dot structure for each of these elements. Okay, so hopefully you pause the video. You got all your elements, you got all your dots. If not, pause the video because I'm about to hit the button that's going to show all the answers here. And so here would be dot structures for each of these elements. So take a look at your work there, see if this matches up. And what we're going to be looking at here is what happens then to these electrons as these things gain and lose electrons, depending on what their electronegativities and ionization energies are. And we will go into our next video and look at that.